I'm going to introduce you that the quite famous interdiffusion phenomena, and we call the Kirkendall effect. This is some kind of application for interdiffusion. Interdiffusion means that the interdiffusion, we have the AB diffusion couple, A bind with B materials. And when I heat these materials up and allow both atoms interdiffuse, then we call and you will find some characteristic inside these materials. Then this we call the Kirkendall effect. But let me explain this. In this case, actually, we have in the beginning we have A materials and wire or bind with B materials, and allow the flux of A atom is not equals to the flux of B atom when interdiffusions happen. Which and then in this case, I assume JA is larger than JB. We have more atoms moves to right-handed side in B materials compared to the B atoms move to A materials. We have more A moves to right-handed side. So we have a JA larger than JB. Then, if you take a look on this interface or this plane, we find that JA larger than JB. But it's weird, right? Why is weird? JA larger than JB is okay, but if only JA and JB and JA always larger than JB, that means after a while, this metal is going to move, right? Move to right-handed side because JA always larger than JB. Then you will get more A here and less B here. So you are going to visualize this materials moves. But we haven't had this chance to visualize something moves, right? During the interdiffusions. And why this happens? So I give you some like theory or something like that. The net flux for each plane, each interplane should be equals to 0, net flux. So based on this case, actually I just replace AB in terms of 1 and 2. We also have J1 larger than J2, but we need to obey net flux for specific plane equals to 0. So even though J1 larger than J2, J1 larger than J2, then spontaneous we have a vacancy flux to balance to allow all net flux equals to 0. So we have a J1, J2. So J2 plus JV equals to J1. So that will then lead the net flux equals to 0. So this is a quite famous rule, something like that. So we have a J1, J2, and JV equals to 0 to allow net flux equals to 0. Okay, and the other quite famous rule is all the atoms move to right-handed side should equals to all the atoms move to left-handed side. So we call a Valenfix rule. So we will explain this later, but you can keep this in mind because this material is not going to move in front of you. So all the atoms, all the valence move to right-handed side should equals to all the valence moves to left-handed side，这叫体积守恒定律。然后这个叫做 net flux equals to 0，也就是说，在任何一个平面上面，基本上它的径的 net flux 都需要等于0。那所以如果 J1 大于 J2，但那个时候你会觉得说，哎，整个系统只有 J1 跟 J2，那 J1 大于 J2 就不合理，因为它就违反了 net flux 等于0。所以这世界上事实上还存在一个你不知道、看不见的 flux 来做这个平衡，它其实就是 vacancy 的 flux，所以才让 J1、JV 跟 J2 会等于0。OK， 那这个蛮重要的，这是第一个在 interdiffusion 要注意的事。然后第二个就是这个刚刚讲的，所有 在互相扩散这件事情，有多少体积的原子往右，就是往多少体积的原子往右移动，就会有多少体积的原子往左移动，否则这个材料就会在你面前像长脚了一样就是移动，这是不合理的，所以就会有这种下面这个叫做 Valen fix 的这个 rule。OK，那 okay, so if you already have this idea, so let's move back to here. So here next we have a flux JA larger than JB. So then we will generate that will lead the vacancy go to spontaneous, go to left-handed side to allow net flux equals to 0. Will allow JV plus JB equals to JA. Okay, so based on these results, this if you explain why Kirkendall effect brings two characteristics. The first characteristic is the Kirkendall void formation at left-handed side because you have a vacancy toward to left-handed left go to sorry vacancy flux move to left-handed side. So that will lead the vacancy formation. This is we call a Kirkendall void formation. And the second term is due to you have more A move to left-handed side, less B go to left-handed side, more A here. This A will push the interface to moves toward to left-handed side. So we also observe the interface moves. This moves we call a Kirkendall interface shift or Kirkendall shift. And in the meantime, in this case, if the A material is Zn and the B material is copper, then you will have the AB alloy or ZnCO alloy, we call a brass. We can observe the brass in the middle. This is a brass alloy. Okay, so what are two characteristics for Kirkendall effect? Is void formation and also the interface shift. Okay. And don't forget the void formation or depending where you can observe the void formation or depending on the direction of vacancy flux. And the interface move to where will be also depending on the JA larger than JB or JA smaller than JB. Okay, so you need to determine based on the JA, the magnitude of JA and JB. And following, we are going to introduce, in order to explain this Kirkendall effect, which means that we need to explain how fast or how slow this interface or void formation, how fast or how slow this interface moves or this void formation. We need to learn the diffusivity, this term, and based on different diffusivity. And we do have different diffusivity based on different coordinate, reference coordinate, and also different material system. 我们刚刚有粗略介绍一下科坑兜乙肺，那它有两个很重要的特征，一个是会形成这种空洞，然后另外一个是它的界面会移动。那它的判断，它的缘由都是因为，像我们刚刚有教大家判断说，当有 A 跟 B 两个不同 flux 的material 在绑在一起，然后当它们互相做扩散的时候，只要 JA 不等于 JB，那你就可以写这样的式子。那我们在这里假设是 JA 大于 JB，那这个时候 net flux 等于0的话 ，vacancy 会往左。那 vacancy 往左的话，就表示你这里左边会形成 vacancy。那因为 JA 大于 JB，然后下一秒钟比较多 A 原子在右边，所以它就会让这个 interface 被推往左边。所以 interface 往哪边跟 void formation 在哪边会 depending on A 跟 B 的 flux 谁大谁小。但为了要解释这 这个 phenomena 就是它这个 interdiffusion 的道理，这个界面移动的快慢，或者是 void formation 的这个状况，我们需要 we need to learn diffusivity. What is the diffusivity, or how to measure the diffusivity? So we are going to explain the diffusivity and how to measure the diffusivity. And here, based on, and as you know, the diffusivity is intrinsic material property to describe how fast or how slow atoms moves inside your materials. And how to measure the diffusivity will be varied on material system, right? If you only have one materials and the diffusivity you have probably is we call a self-diffusivity D star. This diffusivity of component I in a chemically homogeneous medium. Well, so what is this chemically homogeneous medium? Okay, so this is like you have the chemically homogeneous medium and the diffusivity of component I we call a self-diffusivity D star. And at this moment, the chemically homogeneous, which means that you have the uniform concentration of atom I, no concentration variation in these materials. So the diffusivity of this component we call the self-diffusivity. And the driving force actually is just the thermal temperature, nothing special. So actually this materials is doing like the atoms go like a random walk. The average displacement for the atoms equals to 0. So no specific like driving force to acting on these materials because we do not have any chemical potential gradient. And uniform concentration, some people, the first thing materials come out from your mind probably would be pure metal, pure materials. But this material is not limited to pure materials. The alloy is also okay. For example, we have 0.3A and 0.7B. Also, the diffusivity for atom A, also we can call as a self-diffusivity because the also have the uniform concentration of atom A along these materials. No concentration variation as well. So can be the pure material or alloy. So both materials, the diffusivity, we call it self-diffusivity. Okay, is the pure material or alloy. But as we mentioned, the Kirkendall effect actually lays the system is not just pure material or pure alloy, right? We do have A material at, on your left-handed side, B material on your right-handed side is some kind of chemically inhomogeneous. 它的浓度其实不是均匀的。So you can imagine this is ideal case, but the real one we deal with for Kirkendall effect actually is we do have a composition dependent diffusivity of component I in chemically inhomogeneous medium. And this kind of diffusivity we call interdiffusivity, and we use this symbol to represent it. And inhomogeneous, which means that the one we just mentioned is inhomogeneous, means that the concentration distribution are not uniform inside this material. For example, like we have one A material or one material bind with B material or two material. Okay, and in this case, what happens if you heat these materials up or allow the interdiffusions happen? If J1 larger than J2, then we do have spontaneous have J vacancy, move to left-handed side to allow net flux equals to 0. So just quick review, vacancy will be formed at where? Left or right-handed side will be formed at left-handed side, and the interface will move to where? Will move to left-handed side because J1 larger than J2, right? Okay, this is what happened, right? But now, back to here, interdiffusivity D here actually is a diffusivity the observer is stand at where? at lab coordinate, which means that observer or you stand in the lab outside these materials. The diffusivity you measure, we call it interdifusivity. And this is some quite weird, right? Because I specifically emphasize that the observer or you stand outside this material, which means that we only have something, we only have the other one probably stand inside these materials. Okay, so this is the diffusivity. If the observer or you stand at this interface, the diffusivity you measure or you visualize, we call it intrinsic diffusivity. The same chemically in homogeneous medium, but the only difference is the observation frame or coordinate. The observer or you stand at interface inside this crystal. We call it crystal coordinates. So why there will be difference? Because the interface moves during the diffusion. You have the moving coordinate. So if you stand here inside or at this interface, you are moving. So the diffusivity you measure will be different with if you stand outside these materials. So this is the key point. 那为什么会？其实从这里大家就可以知道，interdifusivity 是我们最想要知道的，因为它跟 Kirkendall effect 其实是一样的。Kirkendall effect 其实你的界面也有在移动，然后你其实人是站在这个材料的外面，所以其实这三个 diffusivity 之所以要学习它，最主要是因为我们真正要解决，或者是刚刚有提到说我们要解释Kirkendall effect 的，其实是要用到 interdifusivity。我们是直接站在这个 diffusion couple 的外面，然后想要量测或者是知道这个 interdiffusion 发生的快慢，这个 D。但你为了要回答这个的话，你就要记得是这个材料它本身，它其实它的界面是在移动的。所以你要回答这个的话，你就要慢慢追回去。也就是说，如果因为界面会移动，如果界面没移动的话，那我想就没有太大问题。那我们现在处理的会是界面在移动的状况，所以就会有需要先学习 self diffusivity 是什么，然后 intrinsic diffusivity 是什么，然后最后你才能成功的计算 interdifusivity。所以 following slide we are going to explain how to measure the diffusivity for this three diffusivity, and you are going to starting from D star, then move to DI, then finally you can get the interdifusivity. Okay, so don't forget our target is we want to explain the Kirkendall effect, and the one is you need to get the interdifusivity. But for mathematical calculation or estimation, you need to start from the simplest one, then move to the intrinsic one, then finally get the interdifusivity. And the most important part is our coordinate. We do have a moving interface, so that lead things complicated. Okay, then give you a quick review and hope you already can have some idea between the the intrinsic diffusivity and interdifusivity. Okay, so what we have here is we have a A-B diffusion couple, but in this case, JB is larger than JA. JB is larger than JA. So due to net flux equals to 0, so we have a vacancy flux move to right-handed side. And the second result is due to the JB larger than JA, so more B moves to left-handed side, that will push the interface move to right-handed side. So, okay, so you have the interface move to right-handed side. So if you stand, so this is original interface, and after a while, after like interdiffusion happens, as time increase, the interface moves to right-handed side. Okay, due to JB larger than JA. Okay, so let's give you quick review here. What is the interdifusivity? after a while interdiffusions happen, then interdifusivity means that you stand outside this material and you in the lab coordinate or lab frame, then the diffusivity you measure is we call the interdiffusivity. Okay? And what's the intrinsic diffusivity? Actually is you stand at the interface. And when the interdiffusions happen, because you stand at the interface, right? You move with the interface, but you still stand at the interface. Okay, so the diffusivity you measure or visualize, we call it intrinsic diffusivity. So it's slight difference. Okay, so based on give you a quick summary here. Actually, we learn the uniform concentration one. We have a chemically homogeneous material, so the diffusivity we learn is we call a self-diffusivity. And when the systems move like the chemically inhomogeneous and you stand at the inside the crystal, the diffusivity you measure is we call intrinsic diffusivity. And this one you stand inside the crystal. So you cannot visualize the interface moves, right? Because you stand at the interface. So you cannot feel the crystal or the interface moves. And the interdiffusivity we most care about, we are interested in, is that we call interdiffusivity, which is the diffusivity you stand outside your materials at lab. Okay, so we need to know what are the how to measure three diffusivities as a function of concentration and also with the layer intrinsic material property. And also, what are the relationship between these diffusivities? This is quite important. This is the most important one we want to know, but we need to use this information and can derive to this interdiffusivity. So this is why everything starts from here. So I'm going to introduce self-diffusivity, how to measure that, okay, and how this changes with concentration and also the diffusivity D1 and D2, and move to here. Then that's when we will go here, the most complicated one. Okay, so let's move to the self-diffusivity. For self-diffusivity, the material we have here is either the single compound alloy or single compound materials, or the alloy with the concentration are uniform everywhere. So in order to measure the self-diffusivity, because everywhere the atoms are, I mean, the concentration of atom A and B are uniform, right? So it's quite difficult to measure, right, the diffusivity directly, right? Because the concentration everywhere are the same. So the only way to measure the self-diffusivity in chemically homogeneous material is you use or you implant the radioisotope I star. And so because you label them, then you have chance to visualize or trace uh, their moves, path. So the only way to measure the self-diffusivity is you use the radioisotope I star, and this I star will have the same chemical properties with I. And DI determined from the diffusion profile of I star. So you can consider that a result of random walk process to reach the harmonization of I star and with I. Then, although there's no spatial variation in chemical concentration, but we do have a spatial variation in chemical potential. What this means? Even though you use the I star radioisotope A star to replace part of A, but still they do have chemical potential difference, because the chemical potential of A and A star for sure will be different. Okay, so this is how this also serves a driving force to drive the A and A star mix. Okay, so a process to drive by drive like the diffusions happens actually is increase of entropy and also the mixed entropy between A and A star. So so this is the how to design these experiments can be like some people probably will implant ion implantation to implant radioisotope of A star in these materials, and they measure the concentration profile of this A star as a function of time. Then they can estimate the self-diffusivity of A. But as you know that, as long as you dope or implant A star, this lead you external ended the chemical potential gradient of difference, and this difference will lead the atomic transport. But this is the only way you have chance to measure the self-diffusivity, even though it's not that correct. It's not correct, exactly right, but it is the only way you can do in your experiments. Okay, so the self-diffusivity E will be equals to KT, so Boltzmann constant times absolute temperature, and L11 divided by concentration of 1 minus L1 star 1 divided by concentration of radioisotope 1. And the detailed deviation is shown in page 14 lecture note. Please have a look on it. But at this moment, I hope you can accept these results, and which this result actually just tell you that if you have A materials and radioisotope A, which A star, and the diffusivity, self-diffusivity for this materials A can be expressed like a KT, and this minus this. And if you feel this is hard to like remember or understand, I just give you a hint. Like here, actually, diffusivity divided by KT can be considered as a mobility. Actually, so what you have here is some kind of mobility minus mobility related with radioisotope. Okay, so you can like have this. And here, I just give you a hint, something like that. If you look to the lecture note, how can they derive to these results? They use a net flux equals to 0. So finally, they can get these results. Okay, so some people probably will ask me, like, Professor, need I remember all how to derive to all the deviation steps for like this star? I hope you can take a look on page 14. Just take a look on it and not necessary to memory everything, okay? Because the purpose here is teach you what's the relationship between them, okay? And why in previous questions show in material science and engineering, like the textbook, something like that, the questions they only give us one diffusivity, and without any label, that itself intrinsic or interdifusivity. I just want to explain that. So you're not necessary to memory all the um, details in deviation process shown in page 14. Just have a look and like step by step, read step by step, okay? But if you have any question, just please come to me. Then let's move forward. Now you already have this star show like this. The most important part is this one related with intrinsic diffusivity and further link with um, interdifusivity. Okay, so let's move forward. Okay, so regarding to intrinsic diffusivity, which as we mentioned is you stand at inside your crystal. Inside this crystal, and the diffusivity you measured is we call it intrinsic diffusivity. And just quick remind, we are going to use the net flux equals to 0. So J1, J2 larger than J1, then we have a vacancy flux to allow net flux equals to 0, we'll move to right-hand side. So this interface will be pushed to right-hand side due to J2 larger than J1. So we have more 2 here and push this interface moves toward to right-hand side. And we are going to visualize a vacancy formed at inside material 2. Okay, this is a Kirkendall effect. But back here, this junction will move in upside direction of the flux of faster diffusion component. So the junction or interface move in the upside direction of the flux. The flux is upside direction. So go to right-hand side, okay? And the intrinsic diffusivity, when you stand at this interface, the diffusivity, intrinsic diffusivity you measure will be shown like this. Is quite complicated, right? But if you take a look closely, you're familiar with something, right? This is 1 and 2. How about if I replace 2 with 1 star? It's quite similar, right? If you compare the first term, actually it's similar with this one. Just the difference, one star 1 to become 2 is identical the same. So the first term actually is self-diffusivity, right? And I just use 2 to replace the star 1, radioisotope 1. But let's do additional spatial term. Okay, so what's this term related with? Is 1 plus gamma 1. I see a gamma 1. And this is average atomic volume, and this is the concentration of 8 and 1. So nothing special. But what is gamma 1? Do you remember what's a gamma 1? You learn this in, I remember it's thermodynamics. What is gamma 1? We call it activity coefficient. But if you don't forget, we still have A. When you learn the gamma 1, actually is come with the thermodynamic activity A. We learned that at thermodynamic activity A equals to gamma X. So I give you a quick review here, okay? Thermodynamic activity and activity coefficient Xi. So when you learn the ideal mixing or non-ideal mixing behavior, so give you a quick review. That part is related with Rawls law and Henry's law. When you have AB materials that mix together, we do have ideal mix. So at that moment, A equals to gamma X. And A equals to partial pressure I prime and pressure I0. This is after mixing, and this is before mixing. The vapor pressure after mixing versus before mixing. Okay, and we know that gamma is a function of temperature and composition. So gamma is related with composition. But here, do you remember that if you learn that gamma equals to 1, then A equals to X. So when you try to draw the A versus X, then as long as gamma equals to 1, then A equals to X. So every data point will on this diagonal line. So this means that is obey Rawls law, which is ideal solution. A equals Xi as long as gamma equals to 1. Ideal solution mix, which means that before and after, no matter the equals to 1. So which means that before mixing AB, right? Before mixing, we do have AA bond and BB bond, right? And after mix means that some bonds will become AB bond. So what's the ideal solution? Which means that the bond energy between AABB equals to AB. Okay, so that's not that, which means that you can ignore the bond energy between all the atoms. So this we call, you don't need to consider the bond strength between different, I mean between AB, AA, and BB. So we call it ideal solution, ideal mix. 就是 ideal mix 基本上就是讲说，你可以基本上混合前后它的键的能量或者是键能是没有任何改变，也就是说你不需要考虑它们混合前后键能会不会有不一样的问题。但这个其实大家都可以知道，就是呃，如果你有混合的话，那 AB 的键能是不可能跟 AA 跟 BB 是一样的，所以它叫 ideal 的意思说，就它其实真的不存在，但它可以简化你所有的状况，所以它叫 ideal。所以 ideal unideal solution gamma equals to one, and the other. 那如果 follow this concept, we can know that non-ideal, which means that we need to compare the bond strength or bond energy between AABB versus AB before and after mixing, right? And that the bond energy will affect the vapor pressure. This is after, and this is before. Before is Pi 0. Okay, so there are the other possibility, right? Sorry, if the gamma larger than 1, this is larger than 1, which means that we'll go like this way. At this moment, the A will be larger than X. If gamma larger than 1, then A will be larger than X. So we'll go like this purple line. This will larger than this. Okay, what this means? This means that the Pi prime will be larger than Pi 0, which means that the vapor pressure after mixing will be larger. Vapor pressure larger, which means that AB after mixing, the attraction is lower. That will lead you have higher vapor pressure. Attraction 会是比较小的，所以它才会让蒸汽压比较大。因为吸引力比较小，所以比较多会蒸发，所以 partial pressure will be vapor pressure will increase, so this will larger. Okay, and so the attraction is smaller than before mixing AA and BB. And as we learn that bond energy is more negative, and the system tend to minimize its total energy, so the system will tend to AA and BB become A and BB will be phase separation, and in most of cases this process will be endothermic reaction. Need adsorbed heat. Delta H larger than 0 we call an endothermic reaction. And the other is we show in green. Green is A smaller than X. A smaller than X, which means that the gamma smaller than 1, and which means that the Pi 0 is larger. The vapor pressure before mixing is larger, which means that after mixing is smaller. After mixing is smaller, which that means that the attraction after mixing is strong. So strong, so that will lead the vapor pressure smaller. And the bond energy is more negative, so this is more stable, so the system tend to become component. Okay, so this will be, if you have more AB, then they will more stable, more negative, lead the system minimize, total energy minimize. Then that will be the exothermic reaction, 放热. But just review, okay? just a quick review. What's the A and gamma related with? But the purple and green line are non-ideal solution, which means that you need to compare the bond energy between AB and versus AA and BB. But ideal one is there's nothing difference between all of them. Okay, so back to here, we know that gamma either equals to 1 is ideal and larger or smaller one is non-ideal. Okay, so due to we have interdiffusion happens, we have AB, so we need to based on their like bond energy, then gamma will be different, right? Okay, so then move forward. So you have some pictures, idea of related with that. Okay, so let's in order to simplify these equations, so we take a look carefully on here. This equation we just show you, the average atomic volume for each atoms are constants, not related with concentration. So this will be equals to 0。我的平均的原子体积跟这个原子在里面的浓度其实是无关的，它平均原子体积多大就是多大，所以这项应该是要等于0。然后接着就是 coupling term usually I assume compared to the direct term is quite small, so I delete this term. So I can simplify this results as d1. Oh, okay. And sorry, I can simplify, just copy this one. And I have this term, right? So copy here. And this results actually is D1 star. Because so I can rewrite this results. The first one is D1 star and times this term. But why this is D1 star? If you compare with this one, and I also delete this term, so this is D1 star, right? So this is D1 star. So I find that the intrinsic diffusivity, which you stand at the interface, and to describe how the atom 1 moves is equals to self-diffusivity of atom 1 times this term, which is related to gamma thermodynamic activity. So this I can do further like assume or I can make a further like simplify based on these results. As we learn, if now the mixing is an ideal solution, which means that there is a dilute solution, then gamma 1 will be equals to 1, and it's nothing related with concentration. So under these spatial conditions, D1, which is intrinsic diffusivity, will be equals to self-diffusivity. So only happens in ideal solution or dilute solution mixing. The self-diffusivity will be equals to intrinsic diffusivity. Okay, which means that when you measure the self-diffusivity in material A, 1, then they equals to intrinsic diffusivity, 1, when you stand here and measure the diffusivity of atom 1. Okay? And now I have some idea. As long as like ideal solution, dilute solution, D1 star equals to D1, then what's the relation between intrinsic and interdifusivity? Just the reference coordinate difference, right? Because for intrinsic diffusivity, you stand at the interface and moves with the interface. But for the interdifusivity, you stand outside, right? So when you write down the crystal frame, when you stand here, you don't need to consider the interface moves to right-handed side, right? So you just need to, the diffusivity you measure is based on fixed first law. So you can write that the fixed first law down. But if you stand outside, outside material at a lab, the diffusivity you measure will be different because you need to consider the extra term, which is due to contribute to the interface moves to right-handed side with velocity v will be cv. Why is cv? Actually we show this before, right? Flux can be expressed as CV as long as you know the velocity, right? It's easy as long as you label where your original plan is. Then after a while, you can measure. For example, people use like a laser to punch a ray of holes at the interface, and they can visualize when the interdiffusion happens. They can visualize the array of holes moves. Then you can easily get the velocity of this interface. And this is like we modify the flux because due to our we stand outside this material at the lab coordinate. Okay, so we write down the J1 plus C1V, and the other is C2 times V modify. And as we mentioned, the total volume should be fixed. So J1 prime actually is the total volume moved to right-handed side should be equals to the total volume moved to left-handed side. We have this relationship. This is so you just substitute inside here, so you can get the J1 prime can be expressed like this, and all this diffusivity we call it as interdifusivity. Then the same idea, you also can have a J2 prime, and you got the D interdifusivity concentration gradient. So we got the D interdifusivity can be expressed as D1x2 plus D2x1. Okay, and this relationship actually we give you some introduce you like in where this slide. The Mach crystal plane is moving with the velocity v with respect to n, and this is what we call a volume fix at lab coordinate. You can have this relationship, use this relationship. Okay, so back to here, we know that what's the interdifusivity is related with intrinsic diffusivity. Okay, so I hope you already have some idea why we need to like starting introduce you from self-diffusivity, intrinsic diffusivity, and interdifusivity. Because if you want to know the interdifusivity, you need to know the intrinsic diffusivity. Okay, and if you want to know the intrinsic diffusivity, you need to know the self-diffusivity. Okay, why? Because like here. If you want to know this, you need to know this and also the same here. But I want to explain under some special case. If we assume it's dilute solution ideas mix, we assume x1 is quite small, which means x2 equals to 1. So we got the, here will be, you don't have this one, and this is got 1. So we get the intrinsic diffusivity D1 equals to D, interdifusivity D. So under this special case, which is a dilute solution or ideal mixing materials, ideal mixing solutions, the interdifusivity equals to intrinsic diffusivity. And in previous slide, we also demonstrated that under the same conditions, intrinsic diffusivity equals to self-diffusivity. So that's explained. So actually, under ideal solution or dilute solution, ideal solution mixing case, the in self-diffusivity equals to intrinsic diffusivity equals to interdifusivity. Let's explain why in previous questions, examples you learn in material science and engineering, in the textbook in material science and engineering, they only provide you one diffusivity. They didn't emphasize what types of diffusivity they measure in their systems, because all of them assume under ideal solution case or dilute solution case, then all this diffusivity are the same. So you can you can use a radioisotope to measure the self-diffusivity of your interesting atoms and use this to explain or use this value magnitude to explain and estimate the interdiffusion phenomena. Okay, So I hope you have some ideas. So let's move to some real data to explain the Kirkendall effect. In previous slide, I just show you some cartoon, right? So here is showing your textbook. They grab some data and is hope can explain more about the Kirkendall effect. This is what we have here. Is we have a zinc copper diffusion couples or zinc copper couples, and we heat these materials up. And as we learned before, the the zinc flux is larger than copper. Okay, so that will lead to what happened. We have a vacancy flux moves downward. So you should observe the void formation at the zinc side. And in between this interface, you will have like a zinc copper alloy we call a brass. Okay, so we can have a brass and get thicker and thicker. But if you have have a look on the top panel, and as time increase, you can in the beginning there's a marker in between zinc and copper, and with interdiffusions happens, we can observe the brass get thicker and thicker. Okay, and the marker disappear, which means that actually they move downward, so you cannot see them anymore. And not for zinc and copper case, some people also observe that at the tin silver solder bond, which is connect the silicon substrate to the copper substrate for heat dissipation. Okay, so this solder bond, and they use the copper because the solder bond is bound between the copper to the silicon substrate. So they also observe due to the tin flux, the flux of tin is smaller than the flux of copper. We have a larger copper here, so the vacancy flux will go downward. So you can visualize the vacancy or Kirkendall void form near the copper or near the copper side. Okay, so this is this is a cross section, so you can visualize the void formation. Okay, so this is just for your reference. So so you can see the void. So this is some data uh, to to show you the the interface moves and also the void formation. Okay, besides the AB diffusion couples, you also can observe the Kirkendall effect in metal oxidation process. For example, if you have a copper substrate and you flow the oxygen inside these chambers and heat up the material, heat up the working temperature, as long as the flux of this metal is larger or with the flux of oxygen. And under these situations, you also have chance to visualize the Kirkendall void formation and also the lattice plane shift, which we call that the characteristic for Kirkendall effect. So let's give you some cartoons to demonstrate this phenomenon in these slides. So um, we have a metal, the flux of these metal ions go upward. You can see the metal with positive charge. And because we flow the oxygen, gas oxygen, so we also can observe the flux of oxygen move downwards. And during this process, and the metal will be reacted with oxygen, and we can form the oxide layer on the top of this metal substrate. And in the meantime, as time increase, then this oxide layer gets thicker and thicker. And in the meantime, as we mentioned, the net flux should be equals to 0. at any your interesting plant inside your materials. So due to we do in this case we have a metal flux larger than oxygen flux, so that will lead there's a vacancy flux move downward. They also show that we will have a vacancy, lots of vacancy form or be observed at the metal side. So this, as long as this vacancy get together, then they have chance to form a void. This void we call a Kirkendall void. So you can see that because some metal ion move upward, so we left a vacancy here. And as long as we do have lots of vacancy, they have chance to accumulate, to grow, get larger and larger to form a void. We call a Kirkendall void. And in the meantime, if there's a dislocation inside this metal, or lots of dislocation or crystal imperfection size happens inside your materials, and let's have chance that this vacancy is going to move inside this material. Not vacancy, it will be easier to understand with the vacancy probably will move or exchange with the site, the location with surrounding host atoms, and until probably they will change with the extra atoms in these dislocations. So as long as each of these atoms be replaced with a vacancy, then that will allow the interface shift downward. So this phenomena we call a Kirkendall shift. Also some people call it as a lattice plane shift. So this is the way why we can visualize the Kirkendall void formation and also the lattice plane shift. And in most of cases, you can observe both of them happens. OK，也就是说除了在就是 A、B 的 diffusion couple 之外，其实在金属的氧化过程中，氧化层的生成过程中，其实也是 Kirkendall effect 的例子。那在这样的例子里面，也是因为我的 flux 两个 flux 不相等，导致于我有个 vacancy 的 flux 往下，那在金属这个side 就会形成 vacancy。那 vacancy 它其实有两个人生或选择，一种是 vacancy，因为金属离子离开表面嘛，那还有这个 vacancy，它可能聚在一起形成 void，那它有可能跟旁边的，像是它跟旁边的 host atom 交换位置之后，然后最后换到跟这个多出来的 dislocation 或者是其他，例如说twin structure 或者是point defect 等等，就是换位置之后，那整个原本有多出来的一排像这种 edge 的 location，如果每一个位多出来的原子都跟 vacancy 做交换的时候，那这整排就会消失，所以这个 plane 就会 shift，就会看到 plane shift。所以通常所以这两个都会发生。Okay, but under what kind of conditions you can observe more void formation compared to uh, latest plane shift? Under what kind of conditions? Which also imply that uh, void formation is easier, right? Compared to plane shift. So, for example, if you have more vacancy be generated compared to less dislocation site, which means that the vacancy flux is quite large. Or the void formation energy is small, which means that it's easy to form the void. Or the diffusion, the growth rate of this void is much larger than the diffusion rate of this vacancy, which means that diffusion rate, because if the vacancy because the lattice plane shift actually is this location, the extra atom must be replaced by the vacancy, right? So, and how fast or how slow it will be depending on the diffusivity of this vacancy. If it is quite small, slow, then that will be easier to to get together and form the void. Then you can observe more void formation instead of lattice plane shift. But on the other side, if you really observe more plane shift, also tell you something tell you that, which means that probably our vacancy flux is small, or we do have lots of dislocation inside our materials or our substrate. Or the void formation energy is quite large. That 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 will be so because the void formation energy is high enough, so that's not easy to form a void. Or the growth rate of the void is smaller. It's quite smaller compared to the diffusivity of vacancy, which means that the vacancy is much easier. I mean, move faster, and they'll be easier to replace the location with the extra atoms. Then uh that will lead the lattice plane shift more easier. So for this case, mental oxidation case, you also a typical uh, examples for Kirkendall effect. And depending on which characteristic you observe, you can like have more idea or more information about your metals. If you observe more void form inside your metals, which means that tell you three possible information about your materials. If you observe more Kirkendall shift, that also tell you this informations about your materials. And the last one also, besides this metal oxidation, um, this also is some kind you can consider as applications for Kirkendall effect in order to know more about the diffusivity of zinc versus the copper. What we have here is we have the diffusion couples. On your left-handed side, we have a copper zinc alloy bind with pure copper. And at the interface, we use the uh, uh, molybdenum wire as a marker. When we try to increase the environment temperature above zero point 0.5 of melting point for these materials, then allow interdiffusions happens. Then you visualize the marker move to left-handed side to here. So based on here, these results, you also what can you get from this observation? Or be specifically, um, the diffusivity of zinc is larger or smaller than the copper based on this observation. So on your left-handed side, we have more zinc compared to right-handed side. So the flux of the zinc, when interdiffusions happens, the flux of zinc will move to right-handed side. And regarding to a copper, we have a higher concentration of copper on your right-handed side. So we will have a flux of the copper move to left-handed side. But in the beginning, we have no idea which flux is higher or larger. But after a while, we visualize the marker move to left-handed side. It implies that the flux of the zinc is larger than the flux of copper. So that will lead we get more zinc on your right-handed side and push this marker toward to left-handed side, and also the vacancy flux is also go to left-handed side. In the meantime, I believe you also can observe some void formation at this alloy side, copper zinc alloy side. Okay, so this is like the applications for Kirkendall effect can help you to know the diffusivity for different compound or different materials. Okay, and the last one also is the applications for Kirkendall effect. We call the formation of hollow nail particles and nail wires through the narrow scale Kirkendall effect. Lots of scientists use the narrow scale Kirkendall effect to synthesize the hollow nanoparticles and the hollow nanowires. So I just give you two examples here. For the hollow nanoparticles, how to synthesize this? Actually, uh, in the beginning, you just prepare. We have the core material A as a core and AB alloy as a shell. We synthesize these nanoparticles. And we need to allow the flux of A, JA larger than JB. JB will be inside. The flux will be moved inside, inner. And that would lead you have a vacancy flux move innerward. So you have a vacancy flux moves inward, that which means imply that you have the vacancy or void form inside this A materials. So as long as this vacancy accumulate to form some void, and probably this void will accumulate to form a larger void. And depending on different like the diffusivity of atom A and also the diffusivity and the diameter of this nanoparticles, and also the diffusivity of the surface diffusion. The surface diffusion is the surface here, the inner surface of this void. Then probably they will come out two possibilities. The first one is this void will accumulate and get together to lower the total surface area for this void and form this kind of hollow structures. And we also will have so now what we have here is we have the hollow nanoparticles, and inner layer is material A, then the outer also is AB alloy. And the other possibility would be like instead of form one just large void hollow structure at the center, and they probably would like just prefer to accumulate to form like less four large area and nearby the interface. So this is one possibility. For the case here, the scientists also use the externalize some chemicals to make some holes at the outer at the shell to have this kind of structures, and that will allow them to further to etch this shell, and that will allow them to choose another chemicals to etch this inside, I mean the A materials out to form like this totally hollow nanoparticles and made of like AB alloy. And they can use this to like have as a drug to load the drugs or loaded the other third component inside these materials. So there's lots of possible applications in different areas. So this is how scientists use the Kirkendall narrow scale Kirkendall effect to synthesize the different hollow narrow particles. This for different applications. And don't forget, what drive they have different like geometry of less narrow particles will be the narrow scale Kirkendall effect and also always the surface diffusion. Okay, and the other uh, example would be people use they also use a narrow scale Kirkendall effect to synthesize these hollow narrow wires. So how can they do this? It was like they synthesis the zinc oxide wire with like diameter is like a 10 to 30 nanometers and around the length is up to like 2 centimeters. And they coated alumina on the um, on they coated the thin alumina around like 10 nanometers on this zinc oxide on these narrow wires by atomic layer deposition. And why they do this? Because they want to their design, the idea for this design is based on the Kirkendall effect. They they ap- they they check that they the flux of zinc oxide move outward would be larger than sorry the they allow to zinc the flux outward is larger than the alumina flux moves inward, so that will allow the vacancy flux, the moving vacancy flux move inward. So you are going to have more vacancy form inside this zinc oxide. So then you have chance to get the hollow zinc oxide. You have chance to visualize lots of like void because void will accumulate to form these hollow structures. So finally they form this zinc alumina narrow tubes. So this is also the the uh the mechanism behind this synthesis process is also a narrow scale Kirkendall effect. The criteria here is you need to make sure the flux of zinc oxide is much larger than the flux of alumina. So you have chance to have less hollow, narrow wires for your applications. So I'm going to give you a summary for this interdiffusions part. Diffusivity actually is defined by Fick's law. So if you want me to like give you like the physical meanings for diffusivity can be interpreted at the flux per unit concentration gradient, we call it diffusivity. When you apply a unit concentration of your interesting concentration gradient of your interesting solute atoms or your interesting materials, the flux, atomic flux, the induced atomic flux we call the diffusivity of this solute materials. And in order to interpret the Kirkendall effect we are interested in, we need to learn different three diffusivities classified by according to different um, chemical medians and also the different coordinates. The most important diffusivity we care about actually is the interdiffusivity. But in order to know or calculate or estimate the interdiffusivity, you need to learn what is intrinsic and also self-diffusivity. Then you have chance to get the interdiffusivity to interpret or to explain the Kirkendall effect, which you are interested in. And there are two characteristics for this Kirkendall effect. The first one is the void formation. Okay, and the second one would be the interface or Kirkendall plane shift during this process. So let's finish the first sections.